you have a few options if you want to understand your soil variability in your field. There's two main soil sensors that we use to try and map our soil variability. So we're going to look at the EM survey, which is the most common and probably more typical one that people are most familiar with. So we've got an EM survey map here, and then we're going to add some radiometrics maps. So we generally use three key layers from the radiometrics: the thorium in the top right, the total count map in the bottom left, and then the radiometrics potassium in the bottom right. So this particular view in our software doesn't have a legend key, but it will allow us to superimpose across the maps and compare the maps using some tools in here. So we've got a crosshair tool that might help us a little bit. The first thing you notice is that with the EM map is that the radiometrics maps have different patterns or different structure to them. This is important because it's giving us additional information that the EM map has perhaps not been able to detect, and helps us actually understand where our soil changes are a bit better. So typically the EM looks quite a bit deeper into the profile, and depending on which machine you're using, could be looking up to 1.5 to 2 meters into the profile. But the radiometrics is very much confined to perhaps the top 30 to 40 centimeters and what's going on in the mineralogy in that top part of the profile. So what we're interested in looking at today is some comparisons between the EM and the radiometrics to see if combining the two maps is going to give us some additional information. So we're going to go out in the field and dig some holes and have a bit of a look, but the key areas that I was going to look at is this bottom southwest corner, and if we look at the crosshair, that's a low EM response zone, and it's also a low radiometrics thorium response area. So what we might do is expand that just to two maps so we can see that a bit better. We're dealing in this little area here in the southwest corner. Then we're going to move across here on the EM map in this dark blue area, and we can see it's still, if we look at the crosshair on the thorium, it's still a very low thorium area, but the EM is suggesting that it's an entirely different soil profile, so we're going to have a look at that as well. And then across on the far eastern side, if we look at the crosshair on the thorium map, we're at the opposite end of the scale where that's got a very high radiometrics thorium area, so it's indicating very different surface soil properties, but the EM is actually reading low. So we've got a third type of profile condition that we're interested in looking at. So I'll go out in the field now and we'll visit those three sites and we'll see what we can find under the soil. So what we've done here is we've used the PCT AgMap app on our iPads, and we've downloaded the various layers down into the field, and we're standing in that southwestern corner and we're looking at our location over the top of the low thorium area, and then we can actually then switch on the EM map and we can see it's also coinciding with a low EM response area. So that was one of the areas which we looked at on our maps that we thought, well, this would be interesting to inquire to see what's happening under the soil profile. So we'll dig down and have a look. Okay, so we've dug down the profile in this low thorium, low EM response area, and what we've found is we've got about 45 centimetres of very sandy soil, and then underneath that we're starting to get into some ironstone lateritic gravel. So the thorium radiometrics, thorium sensing, probably detects changes in about that top 30 to 40 centimetres. So that's the main reason why we've got a low reading here, is that it's very, very sandy. Similarly, once we get into gravel, the EM doesn't tend to pick that up and discern very well between gravel soils and sandy soils, so it's sort of suggesting that the profile's all the same, but we've been able to find that gravel down deep. So predominantly this soil profile is very, very sandy, and the radiometrics thorium and EM have been pretty good at picking up that top 45 to 50 centimetres of soil. So now we've moved to the next site of interest, which is only a couple of 100 metres from where we were at our first visit. And why we wanted to come here is that the thorium still suggested that it was a sandy soil, but the EM map was indicating that this profile was considerably different to what was happening in the southwest corner. So the thorium says it's the same, but the EM is suggesting it's very different. So we need to dig down to find out why that is. So there we are over that blue area, and we can see that we're in the low thorium. So that's where we are. So we're going to dig down and have a look, see what we can find. So we've dug down at the second site, and we decided this was of interest because the thorium suggested the profile was still the same, but the EM was indicating that it was dramatically different. So when we dig down through the profile, the first thing we noticed is that we've got a bit better coloured soil in the top. There's some more organic matter, and the soil looks a little bit more robust, but it's still relatively sandy when we get back past for about 6 inches or so. But as we get down further into the profile, the thing that's really different here is that we've got this really massive plasticine type clay, quite solid clay, sitting below about sort of 40 centimetres. So while the radiometric thorium, because it's only sensitive in the top sort of 30-40 centimetres, it wasn't picking up that there was clay underneath. The value of having the EM sensor in this area is that it does look deeper into the profile and it picks up where that clay is. Now, why that's important is because it's going to affect the rooting depth, it's going to affect how much water the profile can hold, and generally the productive capacity of this soil profile. So even though we're about 200 metres away from our first site, the profile is dramatically different, and combining the two sensors has been able to detect that for us, and we've been able to ground truth and verify that there is a significant difference. Okay, so now we're visiting the last site of interest. We've gone to the opposite to the corner of the field, over into the southeast corner. And why we wanted to come here is because the EM was suggesting a very low value, which is supposedly similar to the first site we visited. But what's interesting is that the thorium map that we're looking at here is no longer sort of a yellow cream colour. It's actually very dark purple colour in our map, which is suggesting that it's a very different soil profile. So we can see there that we're in a high thorium and low EM area, and we need to dig down and have a look what's happening under the profile here. So my suspicion here, because of the high thorium reading and what we normally find when we get high thorium levels, is that there's a fair bit of gravel, and I was expecting not to be able to dig down very far into this profile, and that's pretty well what we found. We only were able to dig a couple of centimetres down, and we hit very, very massive gravel, quite large ironstone lateritic gravel, and pretty well impenetrable with the spade, which is obviously going to make it pretty hard for the roots of a crop to dig down as well. So the key with this side here is that the EM doesn't detect very well between sandy soils and gravel soils. But where the radiometric thorium is a huge advantage is it actually detects that very, very clearly, and it's able to show that there is distinct differences between these soil profiles. So by ground truthing it this way, loading them onto the app and visiting it into the field, you can gradually build your knowledge about what the maps are telling you and what that means for real soil type changes in the field. So the advantage of doing these soil sensors is the fact that it can more or less take the soil variability that's occurring in your field and bring them to your office and put them in the computer where you can start to analyse them. The next benefit, I suppose, then is that once you understand where these soil changes are occurring in your field, you can start to look at what that impact is on your yield, what the financial consequences are, and then start to work your way towards some decisions about how you might change your management, either by reducing or increasing inputs, or perhaps doing some soil modification with deep ripping, gypsum, liming and those sorts of things. So soil sensors are very, very valuable, particularly in the West Australian environment. Having both soil sensors together is proving to be the best way to go and providing the most information about our soil changes.